Okay, guys, good morning. So I've got the second part of the hypothesis testing for you. So this will be the conclusion of everything from I guess it's chapter 9. And I'll give you a homework assignment to reinforce this, which will be nearly identical to the examples I'm doing for you. So if you think back to, I guess what was it, Wednesday when I posted the first video for you, we looked at comparing a sample mean to a population mean, and the decision kind of came down to, did we know the population standard deviation? If we did, we use a Z test statistic, so we calculate a Z-score, use that for the test statistic to prove or disprove our hypothesis. If we didn't know the population standard deviation, and we had to use the sample standard deviation to estimate it, then we use the T distribution. Think back to your, make sure you refresh yourself with the stuff we did on Tuesday. But really all it was comparing a sample mean to a population mean, and then whether we know the population standard deviation or not, determine whether we use a T or a Z. Okay, so today just a couple more things. The logic of this is all the same. We're still doing hypothesis testing, but little wrinkles today. Okay, so like I said earlier, we compared a sample mean to a population mean. But one thing that you'll find that you see a lot of this, just because the sociologists were interested in comparing like group means. So, think about comparing men's and women's income, or comparing undergraduates to graduates in terms of the amount of time they study, or you can think of any number of things where you compare two groups on their means, mean income across college graduates and non-college graduates, stuff like that. So you actually see this a lot in the research. I would say of all the things that I'm doing in the, from last time and this time, this is probably the most commonly seen. Okay. So we can compare to see whether these two means are statistically different or are they not. And a lot of you, this will help with when you get back to the projects. I'm just thinking about some of your projects that you'll have different groups and you want to compare the scores, and you can see that maybe they're different, but the question is, are they statistically significantly different? So can we say that a difference of 5 hours spent studying and 5.5 hours spent studying, is that a significant difference, or is it driven by chance? Okay. All right. So again, same steps as before, but this time, we're comparing two sample means, but you'll do the same thing. Make the assumptions, has to be randomly sampled, large enough sample size. Remember, if it's normally distributed, we want at least 30. If it's not, at least 50. Again, that's not a hard rule. It's just kind of a general kind of idea. But I'm not going to trip you up and give you questions. Give you questions where things aren't randomly sampled. It's just not fair. However, there are two different assumptions that we make with the testing with the sample means. The first is that they're independent samples. So if we were comparing men's and women's income, we'd have to have a random sample of women and a random sample of men. How this assumption would be violated is if I took a random sample of men and then asked them to sample their sisters. Or if I was looking at adults and I sampled got a random sample of women, and then I asked them to sample their husbands for the male sample, those would not be independently driven. So the samples have to be drawn independently of one another. The other difference is that there's a difference in the way we state the research and null hypothesis, mostly because we're looking at two means. So we have to, the structure of how we write out the null and research hypothesis will differ a little bit. Okay. So again, let's go through each of the ones and then do an example. Have to be independently sampled. The choice of sample members from one population has no effect on the sample members from the opposite. So my example where I would get women and ask for their husbands or brothers, that would be a violation. So yeah, but we could just take a random sample of say 1,000 Americans and then divide them into groups later. As long as they're independent of one another and there's no, the groups aren't attached, then then we can do this. However, there is a procedure if the samples are not independently sampled. I can show you, there is a way to do the same testing. So for those of you who are doing a project where your independent samples are, where your samples are not independent of one another, there is a procedure doing t-tests where the samples are not independently drawn, and it's easy to show you. I'll just wait and do it on SPSS. So no worries if you have that, but just for now, for the sake of getting through the class, have to be independently sampled. Okay, so the big thing is that there's a difference between how we state the research and null hypothesis, and it kind of makes sense because we're really looking at two population parameters, right? We take a sample of men, we calculate sample statistics to make conclusions about the population of men. And we take a sample of women, and we get a sample statistic for women to make conclusions about the population of women, whether it's in the United States or Georgia or whatever. But just like before, our hypothesis testing, we're always referring to the population, right? I mean, because at the end of the day, that's what we're most important, that's what we're most interested in. We take a sample to conclude about the population. We don't really care about the sample numbers. We want to know if it's representative. So I think this will be pretty straightforward, that if you look at the null hypothesis, so before, rather than having h sub 0, where you have your mu equal to some number. So you're testing to see, well, we sampled this population and we got a mean number of hours of 7.5. Is this, is this indicative of the true population mean? So, look back to the, look back to the slides before. Let's say the old way we did it was mu is equal to some number. And then likewise, that mu is less than some number, greater than some number, not equal to some number. But if we're testing two different means, and we need to account for them both. So our null hypothesis would be, let's just keep using my little thought example, men versus women. Mu1 being women, mu2 being men. So the mean income for men and women is equal, would be our null hypothesis. Again, the null hypothesis is the same, but there's no difference. And we do with the same logic where we assume the null is true until we can prove that it's not. Okay? Same thing as before with the one-tailed and two-tailed. So this will be theoretically driven. On the homework, it will be me asking you for it. But in your own research, if you have a reason to believe, like in this case, we do. We've hopefully y'all are in tune enough with the literature to know that women do earn less on average than men. So if we were if our mu1 was women, we would want to go with a one-tailed test, and it'd be this one that sorry about that little mistake there. Let's correct that just so it's not, because they're both I had them both set at greater than. So this one that mu1 is less than mu2, and this one that mu1 is greater than mu2. So in this case, we would use this one for testing that, the research hypothesis that the mean income for women is less than the mean income for men. Always catching typos on your thing. I guess that's nice to be able to check and change. Anyway, okay, so, and then our two-tailed, just that they're not equal. So the same kind of thing, it's just that you set it up differently. And on your homework, I will ask you to write out the assumptions. I know that's a little bit of a drag, but I think it'll reinforce the assumptions that need to be made. You have to write the hypotheses out. So make sure you're writing it in the correct format. H sub 0 being your null, H sub 1 being your research. Now, if you had multiple research hypotheses, it'd be H sub 1, and then H sub 2, and so on and so forth. Stuff we can talk about later. Okay, good on that. Okay, so perhaps the trickiest slide in today's lesson, but if you think about it, I hope it will become clearer if you sort of let's tease it out a little bit. It's definitely this is the fuzziest slide. So the sampling distribution of the difference between two means. So think back to when we did sampling distribution of the means, the central limit theorem, the M&M thing, all that stuff, where if we took a hypothetical, hypothetically we took an infinite number of samples, that eventually they'd line up in a normal fashion on the true population mean. Excuse me, you guys seemed okay on that. This is sort of the next wrinkle. So this is the idea that if we have what a sampling distribution between the difference between two means, so let's just read through the definition and then kind of unpack it. It's a theoretical probability distribution that would be obtained by calculating all the possible mean differences that would be obtained by drawing all the possible independent random samples of size n, 1 from our sample 1, n2 from our sample 2, from the two populations of different size that are both greater than 50. Again, it's a corollary to the central limit theorem. So rather than plotting a sampling distribution of means where they line up on the mean of means, this time we're creating a sampling distribution where we're plotting the difference between the means. So it'd be like I took one sample of men and women, got their means, and then got the difference and plotted it. And then another sample of men and women and got their difference and plotted it. And another sample and got it and plotted it, and so on and so forth. So if you think about it, if there were no difference, we would have the means, we would have the difference between means lining up somewhere about 0, right? Because if there's no true difference, then they'd be close to 0, or at least the confidence interval would encompass 0. So you can think of if we're doing differences. Let me draw this out real quick. They lining up kind of about 0. Now, certainly sometimes we get instances where, one group made more than the other and other groups made, and then, other where where it was different, because obviously this is negative, this is positive. If this is fuzzy to you, give me an email and I'm gonna have to walk you through it a little bit more, but I'm gonna assume that you understand this, at least for now. But it's the same idea as the central limit theorem. Instead of plotting individual means, you're just plotting the difference between two groups' means. Okay? So really you could plot, women's means along, in a sampling distribution, and then men's means along the sampling distribution. And you could have those too for men and women. But if we're comparing the two groups, we're not interested in individuals. We want to look at the differences. So sample 1, what's the difference? Sample 2, what's the difference? And then plotting those on a sampling distribution. And again, it follows the same logic as the central limit theorem that an infinite number of samples over time is going to line up normally on the true mean difference. Okay, so here's your the equations today. I'm gonna be honest with you. The equations look intimidating, but they're actually really they're a tad tedious in terms of like plugging numbers in. You got to be careful, but nothing in it's real complicated. Again, it's all just addition, subtraction, division, multiplication, and division, and then a square root. I'm going to show you. These equations look scary. I won't lie, but I think once you kind of like get into it, you're going to realize like a lot of it's just the sample size stuff. So just hold off, but. So the sampling distribution, so the mean that we're actually looking at is the difference. So here's the mean difference, right? Before we were plotting the mean of one group or the mean of another group, but here if we're comparing two groups, we want to look at the mean difference. So if we're looking at the mean difference, we're also looking at the difference in the standard error, right? So the standard error for group 1, the standard error for group 2, but if we're comparing the groups, we want the standard error of the difference. So what you can refer to this is the sampling distribution of the difference between means, and then the standard error of the difference between means. That's what we're talking about. So the equation is pretty simple, though. I mean, this is the standard error, the differences is just equal to, and this should look a lot like what you've seen before. Think back to your standard error equation. It's just one part of this. This is the population standard deviation of group 1 divided by the sample size of group 1 plus the standard deviation squared of group 2. Divided by the population size of group 2 and then square rooted. But if you look at this, hopefully you're thinking, well, we don't usually know the population standard deviation. That's kind of the so what of all this. Like, this is the actual equation, but typically we don't know the population standard deviation because that's what we're trying to estimate the mean. So if we don't know the population mean, we're definitely not going to know the population standard deviation. Think back to y, because it's used in the calculation. Point is that in order to do this, we have to do the exact same. Think back to when we were doing a group 1 sample mean compared to the population mean, and had to use and we didn't know the population standard deviation. We had to use the sample standard deviation. To calculate that, remember we had to do some substitution. So here's the same thing here. So rather than the population standard deviation of the difference between the mean, the population standard error of the difference, we do the sample standard error of the difference, right? S versus sigma. And here's the equation for this. And like I said, this is going to look daunting to you, but just take a look at that real quick and look at how many n's are in there. N is just the sample size, and that's easy. So there's not, other than the sample size, standard deviation of population 1, standard deviation of population 2, that's really all that's in there. So it looks complicated, and what you're gonna see is that you're gonna want to write this out and be sort of I guess I don't know what the word I'm looking for is. Just organized, I guess would be the thing to say. Like you're gonna want to go through this step by step. Don't make sure you're writing this stuff out. It's easy to make a little, I guess my point is, it's easy to make a little calculation error in terms of like just forgetting to, and I do this myself actually when I was working the problem out before, I got the wrong answer the first time. It's because I forgot to take a square root. So I think if you write down step by step, it'll be a lot more straightforward. Now, when we're comparing the sample, when we're comparing two means, we use a t-distribution. So I'm gonna, at the end, remember I talked about these 4 kernels within the hypothesis testing chapter. I'm gonna review, because the most common question I get is, when do I use a t, when do I use a z? I've got a nice little trick for that, and I've also got a little website that I think summarizes it very nicely. So here we're gonna be, so if we're comparing 2 group means, we use the t-distribution. When we use a t-test, we got to get the degrees of freedom. The degrees of freedom when we only had 1 sample was easy. It was just n minus 1. This one's not much harder. It's just add the 2 samples together and subtract 2. So that equation shouldn't be too difficult for y'all. Okay. So again, like I just said before, as was the case with as was the case with the single sample mean. So before, what we did on Wednesday, if we didn't know the population standard deviation, if we didn't know the population standard deviation, then we use the t-statistic, right, to estimate the standard error. Same thing in this case, we're going to use a t-statistic. Okay. So we calculate and obtain a t-value that tells us the number of standard deviation units in t that our mean difference, so sample 1, so women's mean minus men's mean, is from the hypothesis value of the population mean for women minus the population mean for men. So it's like what we did on Wednesday, we were looking to see, does the sample mean, is it expected, or does it predict the population mean like in a predictable way? Can we be confident that the sample mean we got is indicative of the population mean? It's the same logic today, but this time we're looking, does the difference between the 2 sample means, is it indicative of the difference between the 2 population means, right? Is the difference between men and women's income from the sample that we got, can we be confident to a certain degree that it represents the true difference in the population? Okay, again, always assume the null is correct. The formula for the t-statistic is easy. It's just x, so your mean of sample 1 minus mean of sample 2. This is the tricky part, because this is the standard error of the differences. And remember, we don't know the population standard deviation, so we can't get the population standard error of the differences. We have to use the sample standard error of the differences and this equation to estimate it, right? Estimated standard error of the differences. Okay. So here's our 5 steps. So what I'd like to do now is work out a problem. Okay. The problem I'm going to use for this one is straight from the book. The last thing we do with the proportions, I'm going to do my own example in the slides, but for now, let's do our book example. So let me move this computer back so I can work out the problem for you. Let's shine it on here real quick. Okay, so the question is from your book, number 11. Okay, so this is in the back of the book, well, not back of the book, but the end of the chapter where you have the exercises. And this problem's worked out because it's an odd problem, but sometimes when they work out the problems in the back of the book, they skip steps. And this one, they skipped a lot, and it looks a lot easier than it is, maybe. But anyway, let's go through this. Okay, so we're going to look at media usage in 2 additional categories, yada, yada, yada. Basically, the question is, so media usage between high school graduates and college graduates. So we have high school graduates, email and TV, and college graduates email and TV. So in this first question, the one I'm going to work out, we want to see whether high school graduates have a significantly lower email hours per week than college graduates do. And I asked to test at the alpha equals 0.05. So we're testing at a 95% confidence level. So if you think about this, what we're doing is seeing, do high school graduates spend significantly more or less or different amount of time emailing than college graduates do? And can we be sure of that at a 95% confidence level, right? I could have specified anything. I could have said 99, I could have said 90, but in this case, we're going to use the 95% confidence level. So the clue here on whether we want to use a 1 or 2-tailed test is whether high school graduates have a significantly lower email hours per week than college graduates. So let's work this out. If we're taking the null hypothesis and research hypothesis, we're going to have the research hypothesis is always the same. It's the mu of high school graduates is equal to the mu of college graduates. Let's just make that C. Mu high school, mu college for email hours. And then our research hypothesis is going to be that the mu of high school emailing hours, and in the question it specifies lower emails, less than mu for college, right? So it's specified in the question whether we want a 1 or 2-tailed test because we want to test to see if high school graduates have a lower email hours per week. And obviously there's a theoretical reason to believe that. Educational differences, we see people with higher levels of education spend more time emailing. I mean, that would be the assumption. But we want to test to see if that's true. Okay? Whoops. That's my cheat sheet to help work this out. Okay, so if you look here, let's get our numbers in order. The mean number of hours spent emailing for high school students is 5.7, I guess this is weekly, 5.71 hours a week with a standard deviation of 7.26 hours per week. And the sample size was 84. Versus the college graduates, we had a sample size of 41. They spent 7.32 hours per week with a standard deviation of 7.23. So you could look at those numbers and say, well, 7.32 is higher. But the question is that difference, could it be driven by chance? Could the sample that we have, maybe we just happen to get a sample of high schoolers that don't email that much. So we want to know, we can see that they're different, but the hypothesis test is to see, can we say with a degree of certainty whether they are different? Okay, so let's go back here. Here's this equation, and this is the one we're going to be working out. So we've got the standard error of the difference in the samples, the standard error of the difference of sample means is equal to the square, and I'm not going to read all that out, you can see it right there. But let's just go ahead and let me work it out on paper. So here's the equation here. So you have the square root of, so we have sample 1 minus 1 times the standard deviation of 1. So that's easy. Our sample 1, I'm going to say that the high schoolers will be sample 1. So you've got 84, 84 minus 1. And then the standard deviation for high schoolers was 7.32, 7.23, sorry about that, squared, plus N2 minus 1 times S2 squared. So our N2 is 41 minus 1 times 7.23 squared. I'm sorry, sorry about that. So we got This is the sample size of 1. The standard deviation of population 1 is 7.26. Sorry about that. Okay, population of 1, standard deviation of 1. Population of 2, standard deviation of 2. Okay, and then it's all divided by n1 plus n2 minus 2, which is the degrees of freedom, if you think about it. But that's just going to be 84 plus 41 minus 2, and everything's there square rooted. Okay, so as you can see, this stuff, it starts to become really long. This is what I'm talking about, where you want to keep things organized. Write the stuff down, keep it orderly, or you're going to make little math errors. Okay, this is easy though. It's just multiplied by the square root of the sample of 1 plus the sample size of 2 divided by the sample size of 1 times the sample size of 2. So that one's pretty easy actually. So we've got, let's get this over, 84 plus 41 divided by 84 times 41. Simple. So see what I'm saying? I mean, it's really just, you have the standard error of sample 2, standard error of sample 1, but then everything else is just the population size. So don't let the equation freak you out or anything. Okay, so let's start working it out. 84 minus 1, obviously, is 83. 7.26 squared is going to be 52.71 plus 41 minus 1 is 40. 7.23 squared is going to be 52.27 divided by, this is going to be 125 minus 2 is 123 square rooted. Multiplied by 84 plus 41 is 125, divided by 84 times 41 is going to be 3,444, square root of that. 83 times 52.71 is going to be 4,374.93, plus 40 times 52.27 is going to be 2,090.8, divided by 123 square root, multiplied by 125 divided by 3,444 is going to be 0.036 square root. See what I mean? With mathematically, this isn't hard, but just stay organized. The easiest thing to forget is to take one of the square roots. Just be really cautious and make sure you're writing the stuff down. Okay. 4,374.93 plus 2,090.8 is going to give you 6465.73 divided by 123. Square root of that times square root of 0.036. 6465.73 divided by 123 is going to give you 52.57 times 0.036. And then when you take the square root of 52.57, you get 7.25. Square root of 0.036 is going to be 0.19. 7.25 times 0.09 gives you a value of 1.38. And hope maybe by the end of this, you're thinking, what the heck is the 1.38? That's your estimate for the standard error of the differences. Okay. So now it becomes really easy, and I'm going to flip to the back of the book and show you where the book made some oversights. But here's the example worked out in the book. Right? Okay. So they make it look really easy, mostly because they skirted this a lot. They didn't show all the steps. All they showed was the 7.25 times 0.19, which was the last step here. They didn't show all the math to get there. That's why I wanted to work this one out, because in the back of the book, it's like, where did these numbers come from? Well, you had to derive them from this equation right here. So everything I've done leads me to this point where I get that 1.38, which is what I got, which is the estimate of the standard error of the differences. Now, go back to the equation to calculate the test statistic is just t is equal to the mean of group 1 minus the mean of group 2 over the standard error of differences. Well, the lengthy stuff we did was the standard error of differences to get this. And then we just plug in, here's the sample mean for high school graduates, the sample mean for college graduates, subtract them, and then divide by 1.38. And you get a value of negative 1.17. Okay, so that's your test statistic. So if you go back to the steps, you've calculated the test statistic. What our alpha that we wanted to look at was 0.05. We computed the test statistic. Now we need to make a decision. So let's go back to the t-table. Appendix C. So remember, we were doing a one-tailed test at an alpha equals 0.05. How many degrees of freedom did we have? Well, what was the equation for degrees of freedom? It was just n1 plus n2 minus 2. So remember, it was 84 plus 41, which was 125 minus 2 is 123. As is often the case, you're going to use this last line because once you go above 120, the differences become kind of moot at that point. But we're looking at that one-tailed test, 0.05. Your significance level, your cutoff point is 1.645. So we have a t statistic that we derived that was negative 1.17, right? And then we had based on our alpha equals 0.05, a cutoff point of 1.645. Now, just like the just like the Z table, the T table also is symmetrical. So we're really it's really the negative 1.645. So if you think, it's kind of the same thing as if you had 1.645 and then negative 1.645. Remember, they're symmetrical, so we can always test positives or negatives depending. Now, where this all would come to is if I would have made the college group 1 and the high school group 2, we would have ended up with a positive 1.17. So positive and negative doesn't really matter. But the key is, and this is kind of the so what point, if your test statistic is lower than your alpha level for T, then you fail to reject the null, right? So this the test statistic that we got, 1.17, is less than this number. If it doesn't go above that number, then we can't accept the null, meaning that, let's flip to the book just so you can see. The obtained T, 1.17, with 103 degrees of freedom, the T obtained is less than the T critical. So if the T statistic that we get is less than the critical value, we fail to reject the null, meaning we accept the null. So in real words, how we would say it would be, we're 95% confident. Go back to this. We are 95% confident that the true mean difference between college graduates and high school graduates is they're not significantly different than each other. Meaning that we're 95% confident that the true mean difference is not significantly different than 0. In other words, we can't say with any certainty that high schoolers and college students, or college graduates and high school graduates, email at different rates, okay? Had this T statistic been higher than our critical value, then we would reject the null and say there is a difference. But if this number is less, and this is gonna hang people up, I know it, but just with the T, if we have a T statistic that's less than the critical value that we generate, the T statistic we generated compared to the critical value, which came from the alpha level, which we looked up in the book, if it's less than it, we go with the null. We So, looking back at our thing, if we're going with the no, we would say that the mean number of email hours for high school students is equal to the mean number of email hours for college students. And we're 95% certain that that's the case. So this would be a fail to reject the no, AKA accept the no. We're going with the no. We weren't able to, it was like the person's innocent. We weren't able to prove them guilty. Okay. I'm going to close this and then do the last one. I'm going to stop the video here and then upload another video because I've had trouble with anytime the video goes over 30 minutes, I've had trouble uploading it. So let me pause this one and then go to the next.